Hi everyone, and thanks for staying. I'm Jonathan, and the purpose of this talk is to introduce you to the new programming language that we've been designing with my advisor, Protzenko. And we're not the first ones to design a new language, but hopefully I'm hoping that I'm going to be able to convince you that there are some valuable ideas in it. So it's going to be a very hands-on session. I'm going to give you examples, and if something is unclear, please feel free to interrupt me. So first of all, what is the purpose of Mezzo? So Mezzo is strict and impure. So it's in the tradition of ML, which sounds reasonable for the ML workshop. It has control of side effects, aliasing, and ownership. So we really want to go beyond the type checking of ML and offer stronger guarantees. And the thing that we have with Mezzo is that whenever things get too complicated to be expressed in a static type system, we decided to go with dynamic checks, which allow us to strike a nice balance between complexity and expressivity. And the interesting thing with Mezzo is that there is no effect system that comes on top of the type system. It's all fused together with a concept that we call permissions. And I'm going to tell you right now what a permission is. So we don't say variable has type tau. We say we have a permission to access variable y with type tau. In that case, when I write the snippet right above, that generates a tuple, that's a value, a tuple, just like in OCaml, for instance. And we say that you are granted the permission y at string, comma, int. That means you can access variable y with type string, comma, int. You can think of an access token. These do not exist at runtime. These exist purely in the type system. And whenever a function wants to do something with a variable, it requests a token and grants you back the token if it doesn't need to keep it. So let's consider the length function, the usual length function. That's nothing fancy. So it's for all a, that's our notation for all, it's not a list. It takes an argument called y, which is a list a, and it returns an integer. And as a convention, we understand that function to both require a permission y at list a and return that permission at the same time. Because what the function does is it grabs access to y, runs over it to find out how long it is, and then returns to the caller the permission on y. And at the same time, it produces value of type int. Let us see now a more sophisticated example that will hopefully justify why we think in terms of permission. This is the x swap function. It takes a pair that is mutable. It has pairs have a left field, a right field, and we swap in place those two fields. The function does not return a new value. It swaps in place the existing value. And the interesting part here is that unlike the previous length example, the function does not return the token that says y has type pair AB. Instead, it consumes the permission, and it does not return that permission to the caller. What it does instead is return a fresh permission saying, now what you are granted is a token that says y now has type x pair BA. And the cool thing that's happening here is that y has changed type. It was an x pair AB. After we call x swap, it's an x pair BA. And the question is, how come that example is sound? We cannot do that in ML. That would be unsound. So how come that at some point we have y at x pair AB, the permission, and that afterwards we get a different permission, y at x pair BA? The reason is that example is sound if no one else can see y. So if you create y with type x pair AB, you call x swap. The set of permissions you have changes before and after the call to x swap. And now we see that permissions are not exactly like types. They can change. And if we want that snippet to be sound, we must make sure that only one person can access y. Otherwise, we would break someone else's assumptions. Yes?
So you keep on saying, to person has the right, but like, what is the actual entity that has the permission?
It's the point in the program. At a given, I'm sorry?
Just a code.
Yes, exactly. At a given point in the program, you have a set of permissions that is available. And if you call a function, the function will operate on that set of permissions and make that set of permissions change. And when I say someone can see and no one else can see, I'm thinking threads concurrency, and I will come to that later. But in a sense, the permission mechanism allows you to control who owns the right to access a given location in the heap. And that is very important whenever concurrency comes into play. We'll get to that later. So right after the let binding, at that program point, permission y at expert AB is available. And after we call xswap, the set of permission changes and the new permission appears instead. So there should be no aliases to y for that example to be sound. That's why we have different types of permissions. Things that are mutable are uniquely owned. Only one person can see them at a time. So because those pairs where we swap the components are mutable, the type system statically guarantees that only one person has a permission for a next pair. That means it's sound to change the permission on a next pair because you're the only one seeing it. No one else can see that pair. So no one else is shocked by the fact that you just changed the type of the pair. And for things that are read-only, like integers, strings, those are said to be duplicable. They're read-only and they're shared. What does that mean for permissions in practice? That means that some permissions can be duplicated. Like if you have a permission that says that y is an integer, you can create another copy of that permission and pass it to another function, and that's okay. However, if you have a permission that says y is an x pair, then you cannot copy that permission. You can only pass it to a function, but you cannot create a second version of it. That's what enforces the fact that only one person at a time can see some mutable object. So that's where the X comes from. The X comes from exclusive. We say that y at expert is an exclusive permission because we have exclusive access to the memory location that holds the pair. For those of you who are aware of it, that is similar to separation logic. In separation logic, to say that whenever you have a conjunction between two separation logic statements, this conjunction is separating. For instance, when you have y at tau and z at tau, and you do the conjunction of those two permissions, if tau is something that is exclusive, that is something that is mutable, then you learn that y and z are distinct. They point to distinct locations in the heap because objects of type tau cannot be shared. They cannot have multiple pointers to them. So that is a must-not-alias constraint. So whenever we deal with mutable portions of the heap, our system of permissions is just like separation logic. It is separated. However, we extend separation logic in the sense that we have that notion of immutable things on top of the usual separation logic concepts. So what does it mean if you say that y has type tau star z has type tau when tau is duplicable? That just means that the permissions have to be consistent with each other. If you have x at end, star x at end, that's consistent. That's what you learn. So we extend the star conjunction of separation logic. Internally, how do we represent permissions? That is the definition of the mutable pairs that I've been talking about. A mutable pair is just a record with a left field and a right field, and it's declared as being exclusive. Exclusive means uniquely owned, thus mutable. Let's see how this is represented internally. When you say that y has type x pair, what you can think of is a drawing. There's a block in the heap with a left field, a right field. The left field points to another location in the heap that we may name L, for instance, which has type A, and the right field points to another location in the heap. we make those aliasing relationships explicit in the set of permissions. If you have permission y at x squared ab, what happens is that you can refine automatically that permission, saying, well, actually I know that y is a record with a left field and a right field. And what happens afterwards is that internally we make the points to the small arrows in the drawing, the arrow that points to L and the arrow that points to B, we make them explicit. We say there exists, and here the type checker automatically picks a name for the left component of the pair. We say there exists a given location called L. L has type A. There's another location called R. R has type B. And Y is a record whose left field points to exactly the same location that is that of L, and whose right field points to R. And that's exactly the drawing that we had before. So internally, we manipulate a tree of aliasing relationships. We just saw the equals something type. That's what we call a singleton type. When we say that Y has type equals Z, that means Y and Z point to the same memory location. And just like the conjunction makes must not alias constraints explicit, the singleton type makes must alias relations explicit. You know that Y and Z are aliased. So that allows us to use some syntactic sugar. For instance, we write Y at x squared left equals L instead of left colon equals L. And instead of saying Y at equals Z, we say Y equals Z. So, yes?
Do the restrictions about readability and exclusive access mean that some kinds of data structures are just strictly out of bounds with Mezzo? For example, strictly out of bounds, like inexpressible language. The example I'm thinking of is you have a collection of mutable objects,
yes,
and then you have multiple indices, right? Which is a very common structure.
You mean several things point to the same mutable object?
Yeah. So, for example, imagine, for example, I want to implement like a priority queue where I can pull up things out.
Well, I'm glad you're asking, because my next example is a queue. I didn't ask him to ask a question. That's purely a coincidence. So, of course, there are some patterns that you cannot express with that very simple mechanism of aliasing that points to relationships. Examples are a mutable doubly linked list with arbitrary length, or a list where you have the same element twice. If you have the same mutable element twice in the list, there's two pointers to it. You can access it through two different paths. So that's not expressible in our static system. And that's precisely where we drew the line. For those complicated patterns, instead of having super fancy types that express the fact that it is sound, we decided to go with dynamic checks. So we don't pollute the static type system, but instead we do dynamic checks to make sure a mutable object cannot be owned by two people at the same time. So the things that we cannot represent are precisely mutable heaps with arbitrary shape. And the example that I'm going to use in that part is a queue, a first in, first out queue, a FIFO queue, where, for instance, the last cell is accessible through two different paths, through the head, and then following the next pointer in each cell, and through the tail of the FIFO. So the aliasing pattern here is there's a header object in blue that points to the first element and the last element of the list. Each one of the cells is mutable. You can mutate the next field, and the last element points to itself, so that you do not have to put an option type in the next field. So how do we do that? We say that an object can adopt other objects. And what that means is that you give up the permission for a small cell, and instead you hide it inside the permission for the header object with the first and last fields. And when you own the FIFO, the header object, you also own the small little object. So you conceal the permission for a cell inside the permission for its adopter. So instead, what that allows us to have is to have a hierarchy of adoption. The small sets are all adopted by the FIFO, which may be in turn adopted by someone else. And now we recover an ownership tree. Sorry, it's not a graph anymore. The ownership diagram is a tree. So imagine you have X, which is a cell. You have F, which is a FIFO. And you cannot endless X, because cells are mutable, so they're uniquely owned, and you cannot duplicate that permission. What you do is, okay, I'm given enough X, I'm giving it to F. And the set of permissions that you obtain afterwards says that X now has type dynamic. Dynamic means you don't know the true nature of that object. However, you can copy it. Dynamic is duplicable, so you can copy it, alias it, but you cannot do anything meaningful with it because you no longer know that it's a cell. And the converse operation is called take. You have X, you have F, which is a FIFO, and you say, I assert that, first of all, X is adopted by F, and I also assert that no one else currently owns X. So now please give it to me. And what happens afterwards is that you regain the original permission with the full information that X is a cell. And of course, we need to check that no one else actually owns X, and that involves a dynamic check.
So where is it apparent from that you want to take it back as a cell?
I'm sorry?
Where is it apparent from that you want to take it back as a cell? You might change its type.
Oh, the question is, how do I know that the type I gave is cell A? So it's right here when you declare FIFO, you say that FIFOs adopt objects that are of type cell A. So the type checker at that stage looks up the definition of FIFO A and then allows you to, yes.
So what if F adopts things of several types? Can you then say you take?
No, that
you can
can
only
be
adopt one type.
That's an option we have considered, but FIFOs can only adopt one given type of objects.
Okay.
Otherwise, it would be an unsound option. So how is that implemented in practice, the dynamic check? What happens is that cells have a hidden field, which is the address of their adopter. So the field is set when you put the small cell inside. When you give the cell to the FIFO, you mutate that hidden field and you make it point to the FIFO. And when you want to take it out, you check that the cell actually points to the object you are taking it from. And afterwards, you null out the field. So there's a write when you give the cell to the FIFO, and there's a read and a check when you take the cell from the FIFO. And of course, the addresses must match, and that's how you implement it in practice. And now, during the remaining minutes, I will explain in a step-by-step fashion an example function to tell you how those mechanisms work in practice. So back, FIFOs implement the following interface. You can create a FIFO. The function returns you in your FIFO. You can insert an element in a FIFO. There's a consumes annotation that says that you give up the ownership for your element to put it in the FIFO. And when you retrieve an element, you may get an A object. The option is here because the FIFO may be empty. So here's the code for the insert function. And I'm going to type check it in a step-by-step fashion. So on the top left corner, you see the permissions that you cannot copy. And on the top right corner, you see the permissions that are adopted. So when you start and you enter the function, you have two arguments. The first one is X, which has type A. The signature requires that. And the other argument is F, which has type FIFO-A. And for that function to type check, we must make sure that whenever we reach the end of the control flow for that function, because FIFO-A is not marked as consumes, it must be returned. That's normal. You call insert, you're the caller. You expect the insert function to give back to you the permission on the FIFO. So insert consumes the element that it's inserting, but is returning to the caller the right to still use the FIFO. So we create C, a cell. Its data field points to X. Its next field has type unit. We mutate the next field to make it point to itself. That's the trick not to have an option type for the last element of the FIFO. So now the permission reflects the fact that the next field points to C. And we're going to put that element in the region. So we say that we're going to give C to F. for that, we must make sure that C is a cell A. So we first fold back the type of the cell into cell A, the nominal type, and that's exactly the type of elements that can be adopted by F. So we actually perform the adopt operation. There's a typo here, you should read give C to F. I'm sorry about that. So now, once you've given C to F, C before had type cell A, and now it has type dynamic, which means it can be aliased, and you can copy the corresponding information. And now, we have two different code paths depending on whether the FIFO was originally empty or whether the FIFO already has an element in it. If the FIFO is empty, we're going to refine the permission on F, and we're going to learn the fact that F is empty. Here we go. We just learned the permission changed. We just learned that F is the empty FIFO. What do? We mutate its tag, so the tag changes, empty becomes non-empty. What we do next? We say that the first element is also the last element, and is simply C. So head changes, tail changes too, and that can be folded back as a FIFO. And because the function needs to return F as being a FIFO, that's just fine. That satisfies the expected return type for the function. In case where the FIFO is not empty, we take the last element, so that should read take tail from F. So we take the last element from F. The tail has type cell A, which the type checker automatically unfolds to cell with the data field and the next field. We say that now the last element is C, so we rewire the last element to point to the cell that we just created. And we say that we can put back tail into F. So we read give tail to F. Tail has type cell A, it can be given back to F. And now we do the final rewiring step. We say that the cell that we just created is now the last element in the FIFO. Is F a FIFO? Yes, it is a FIFO. So the return type for that function is satisfied as well. Let me now give you a few words about how far we've gone with that language. The areas that are going to need work in the immediate future are concurrency. We have some ideas in mind for concurrent separation logic. There is some work involved for inference, especially in presence of polymorphic function calls. We need to infer the polymorphic parameters, and that turns out to be not as easy as it sounds. And we have a proof ongoing of type soundness and type preservation, and we hope to have that proof ready as soon as we can. We have a prototype that successfully type checks easy examples. We may write an interpreter later on to actually run the programs, and we have better ways to report error messages. I'm now going to show you a very, very small example because I'm running out of time. And that should hopefully convince you that it's not a fake language, that it actually exists. So here's a Mezzo program. It's really super simple. We have pairs of units because I didn't want to get fancy. And we have a function that takes a pair and returns you a tuple with two pairs. So here, pair does not have the exclusive keywords. So those pairs you can copy because they're not mutable. So it's okay to put an element, create a tuple with the two fields in the tuple that point to the same element, and return that. So does it type check? Fingers crossed. So yes, it gives you the final set of permissions you obtain after you type check that program. It's not very readable because that's the internal representation for function types, but the program type checks. Let us now see what happens if I put an exclusive keyword here. Exclusive means that you won't be able to copy the permission on X to put it in each field of the tuple. So that function will actually fail to type check because you're trying to copy an exclusive permission. So I'm running it. And what happens, is that I have a very fancy error reporting mechanism that tells me, oh no, you didn't get to type check the program. So it actually highlights the location where the error happened, and it gives you, more importantly, the aliasing graph that it has understood so far. So here, that is the return tuple appearing here for the function, and the type checker knows that both fields point to the same memory location, which is a pair, and that pair comes from that exact location. And we now understand why we were unable to match the expected return type of the function. That's because we're trying to share something that cannot be copied around. And with that, I'll take any questions.